On this worksheet, we're going to solve a variety of different problems about chemical equilibrium. The first problem is giving us a reaction that is in equilibrium, or that can exist in equilibrium, as telling us that we are starting out with 210 millimoles of H2 gas and 210 millimoles of I2 gas. And then it's asking, when the system reaches equilibrium, what will be true about the amount of H2 gas. So since it didn't say anything about HI, we can assume that we're starting with no HI at all. That means that the position of equilibrium is going to move to the right. Some of the H2 will be reacted, some of the I2 will be reacted in order to produce HI. So that means that when we get to equilibrium, we are going to have some number less than 210. Some of that 210 millimoles are going to get reacted. We don't know exactly how much, so we're just going to choose this number right here, less than 210. Here's another problem very similar. With this reaction, it says that we are starting with 115 millimoles of HI, no H2, no I2. So as the system reaches equilibrium, that means that the position of equilibrium will shift to the left. We will lose some of this 115 millimoles. At the end, we will have some of that 115, but we will have less than whatever we started with, less than 115, which is going to be this number right here. Now we are able to actually calculate the amount that we have of each substance in equilibrium. As long as we know the equilibrium constant, we can be a little bit more specific than just saying less than 115 millimoles. We're going to practice that on this next problem. So this problem is telling us that we have SO2 and O2 in equilibrium with SO3, and we are starting with 0.1 moles of SO2 and 0.7 moles of SO3. And we want to calculate the final molarity of all three of these substances. So it's not asking us to make a prediction, it's asking us to actually calculate it. To do these types of calculations, we're going to use a tool called an ICE table. That stands for Initial, Change, and Equilibrium. We're going to begin by filling in the initial concentrations of all three of the substances, and these everything in this ICE table needs to be in units of molarity. So the problem is telling us how many moles we have in our volume, but we need to figure out what that is in terms of molarity. For SO2, the molarity of the SO2 is 0.1 moles per 0.5 liters. I'm getting that information from the problem, which is 0.1 divided by 0.5 is 0.2. So that's 0.2 molar. We don't have any O2 at all, so it's not telling us anything about the O2, so that's going to be a 0. And then for our product, SO3, our molarity is going to be 0.7 moles, also in 0.5 liters, which is 1.4. So in the next row on the ICE table, we're going to fill in the change to this, how much is actually reacted. For the SO2, because it's a reactant, our change is going to be negative, and because its stoichiometric coefficient is 2, our change is going to be negative 2x. For the O2, also because it's a reactant, it will be negative. The stoichiometric coefficient is 1, so this is just going to be minus x. And for our product, because it's a product, our change will be positive. Stoichiometric coefficient is a 2, so this is going to be a plus 2x. And at equilibrium, we're going to have 0.2 minus 2x of the SO2. We're going to have negative x of the O2, and we're going to have 1.4 plus 2x of the SO3. Now you might be saying, oh, this is impossible. We can't have a negative concentration. This doesn't look good. Well, as we solve for x, when we get to this point, the correct x is going to be a negative number. So maybe we're going to find that x is negative 1. And then for this, to solve for the amount of O2, we're going to say it's negative x, which is going to end up being a positive number. So if you're worried about this negative term, don't worry. It's going to be okay. So all we have to do is find the actual values of x, and that's going to give us the equilibrium concentration. If we know the value of x, we can just plug it into this equation right here, and that will give us the equilibrium concentration of SO2, and we can plug x into here, and that'll give us the equilibrium concentration of SO3. And the way that we come up with these equilibrium concentrations, or excuse me, the way that we come up with the value of x is by using an equilibrium expression. Writing an equilibrium expression for the equation, remember that this is going to be products over reactants, each one raised to its own stoichiometric coefficient, leaving out pure liquids and leaving out pure solids. So we're going to set something up like this. And then all that we need to do is plug into every single one of these terms in this equation. We need to know everything. Now, one of the problems here is that in order to be able to solve this problem, we need to know what the equilibrium constant is. And unfortunately, it's not provided to us. So we actually are not going to be able to solve this problem. We're just going to be able to come close. So we need to know what the Kc value is, but we can set this problem up a little bit further. What we're going to do is, instead of writing SO3, we're going to write the actual term for SO3. So that would be 1.4 plus 2x, and then don't forget that that needs to be squared. And then for SO2, the term from the ICE table for SO2 is 0.2 minus 2x, and that needs to be squared. And then the term for O2 is negative x. So we've got this all set up, and we're going to set it equal to whatever the value of Kc is. So the problem would tell us, like maybe the problem says that Kc is 10. That means we're going to set this equal to 10, and we're going to solve for x. This is going to take a lot of algebra. It's going to be pretty tricky. You can do it. I'm not going to do it here because I don't want this video to be half an hour long, but you know how to do these problems, to solve these problems. You just have to, remember how to do that. Remember your math. Let's take a look at another problem that's kind of similar. It's not exactly the same. In this problem, we are given the equilibrium constant. So our equilibrium constant is right here, and it's giving us some initial concentrations or initial pressures of all of these substances. And it's asking us to determine which of these substances will increase as the system approaches equilibrium and which ones of them will decrease. So since we're not being asked to do an actual calculation here, we don't need to use an ICE table. We could if we wanted, but it's not going to be necessary. We really only need to use ICE tables when somebody's asking us to calculate a specific number. If we're just making predictions about increase versus decrease, the easiest way to do this is to use the reaction quotient, Q. Now remember Q and K, this is something that confuses a lot of students because Q and K are really similar. One thing that's similar about Q and K is that they are set up and calculated in the exact same way. So they are both going to be products over reactants, each one raised to their stoichiometric coefficient. So to solve Q, we're going to use an equilibrium expression set up in the exact same way, like this. And as I'm writing this, I'm remembering, when I started writing this, I forgot, I'm remembering that these are actually gases, not molarities, but I'm just going to leave the brackets because the setup is the same. So Q is calculated in the exact same way that K is calculated. Let's just go ahead and calculate our Q. We're going to plug in from all the data that's in the problem right here. We're going to plug in our concentration of N2, our pressure of N2, which is 2.45 atmospheres. We're going to plug in the pressure of the H2O, which is 5.60, and don't forget that it's going to get raised to the 2. And we're going to plug in our pressure for NO, 9.26, also being raised to the power of 2. And then our pressure of H2, 10.79, also being raised to the power of 2. So we're going to solve all of this. We're solving for Q, which is mathematically the exact same way that we would solve for K. The big difference between Q and K is that K is only used when the system is in equilibrium. So right now I'm just doing the math on this. I'm at the 9.26 to the 2 divided by 10.79 to the 2. So this works out to be 0.0076 0.0077, we'll say. Our value of Q is 0.0077. It's not the same as the value of the equilibrium constant. Notice that those are two different numbers. Although sometimes Q and K could be the same. If we calculate Q and it is equal to K, then that tells us that the reaction, Rxn, my abbreviation, the reaction is in equilibrium. So if we calculated a Q and the numerical value of the Q was K, that would tell us that the numbers that we had plugged in to that equation, those numbers were equilibrium concentrations. And most of the time Q is not equal to K. Most of the times it's either greater or less than. In this case, our Q is less than K. Now, sometimes Q could also be greater than K. So when Q is less than K, like what we have here, what does that mean? You know, mathematically, what does it mean? It means that in our equilibrium expression, the numbers up on the top of our fraction are too big, or the numbers on the bottom of our fraction are too small, or maybe it's a combination of both. These numbers up here are too... No, I said that completely backwards. When Q is less than K, the numbers up here are too small and the numbers down here are too big. The numbers up here being too small means that the concentrations of N2 and H2O are too small. The concentrations of our products are too small. So when Q is less than K, that means that we need more products. And in order to get more products, the position of equilibrium is going to move to the right. When Q is larger than K, this means that we need to have less products. We need to use some of them up. And the position of equilibrium would be shifting to the left. So the question is specifically asking which of the things will increase. Well, we need these guys to increase, these guys right here. So our N2 and H2O, those are the ones that are going to increase in order to get Q to be larger and larger until it gets all the way up to K. And our reactants, they are too big, so they need to decrease. For the next problem, now we're kind of shifting gears a little bit, and we are going to be using equilibrium to help us calculate non-standard delta G values. This particular problem I have already solved in video number 60, so I'm not going to solve it again right now. And if you want to see it solved, go to that video. We are going to solve a very similar problem, this one right here. So this one we're calculating non-standard delta G, and there's a few steps involved in calculating non-standard delta G. First, I'm going to write the equation that we're going to use. Non-standard delta G is equal to standard delta G plus R, the gas constant, times T, the temperature in Kelvin, times the natural log of the reaction quotient. So the first thing that we're going to do with this problem is calculate the standard delta G that we need in this equation, and the easiest way to do that is using Hess's law. We have our delta G values right here for us. Hess's law is products minus reactants. So our standard delta G is going to be the delta G for our first product, aluminum. That is negative 1147.25. These are all kilojoules per mole. And our other product, we have three of them, the OH, and that's this one right here, negative 157.3. And then from that, we're going to subtract the delta G of our reactant. Oh, it looks like I plugged the wrong one in. Back up. I plugged in the wrong value. Al3 plus delta G is negative 481.2. Okay, and now our delta G for our only reactant, that's the negative 1147.25. So let's calculate this. Negative 481.2 minus 3 times 157.3 minus negative 1147.25. This is a standard delta G of 194.15, and the units are kilojoules per mole, and this is a positive number. So that's going to be this piece of the equation. We know the value of R, it's a constant. We know the temperature, it's 25 degrees Celsius, which is 298 Kelvin. And so now we need to know what Q is. Our next job is to calculate Q. Like we just practiced this, Q is calculated the same way that we would calculate K. So we need our products over the reactants raised to their stoichiometric coefficients. And don't forget that we leave out pure solids and we also leave out pure liquids. So the Q for this is going to be Al3 plus times OH minus cubed. We're going to plug in our concentrations from the problem. Our aluminum concentration is 0.578. And our OH minus concentration is 0.388, and that's going to be cubed. So let's calculate that. And this gives us a Q value of 0.0338. These problems are pretty tedious, but now we're ready to actually finish it off. We can calculate delta G, non-standard. We have all of the information that we need. We're going to plug in our delta G standard value, that is 194.15 kilojoules per mole. And then to that, we're going to be adding the value of the gas constant R. In this particular type of problem, the value of R that we use is 8.3145 joules per mole Kelvin. It is the same R as the ones that we've used before, 0.08206. It just has different units. So the liters atmosphere unit has been converted to joules. These two are the same constant, just again with their units being switched a little bit. So the R we're using is 8.3145 joules per mole Kelvin. The next term in this equation is the temperature in Kelvin, 298. And the last term is the natural log of the Q that we just calculated, 0.0338. We are going to have a little bit of a joule to kilojoule incompatibility going on here, so we're going to have to be a little bit careful with that, which is why I'm going to do this in two separate parts. I'm going to solve that 8.3145 times 298 times the natural log of our Q. This is negative 8396, and my units are joules per mole Kelvin. Nope, my Kelvins canceled out. I forgot to write that down. Joules per mole. So we need to do a joule to kilojoule conversion. 194.15 kilojoules per mole minus 8.396 kilojoules per mole. And we are going to get, not a huge difference, 185.8 kilojoules per mole.